Hi guys, back doing our third video, just following on from where we left off last time, talking about pressure balancing shock absorbers and forks on your bike. So I thought that the best place to start would be this quick tech sheet from Penske, and just see what they say about the subject of pressure balancing. So they say here the pressure balancing of shock absorbers is a new method of optimizing a particular damper setup for a particular track or target velocity to reduce hysteresis and improve grip while still avoiding cavitation. They say it's a lag in pressure across the main piston. So I think it's important to note that they say here that hysteresis and cavitation are obviously two different things. So we can clearly see that hysteresis isn't attributed to cavitation. So I think that's important to note. They go on to say that pressure balancing is the method of making external and internal adjustments to the damper to achieve a symmetric pressure differential of compression and rebound pressures, i.e. the pressure differential across the main piston. This coincides with the percentage of overall compression force attributed to the head valve being 7 to 13%. So I worked out based on the numbers on our WP shock that we probably want that around 14%, just based on that 6.7 to 1 ratio. And obviously that will vary. It's depending on the shock body size and the shock shaft size. So if you're running a 16mm shaft, that ratio is going to change a little bit compared to an 18mm shaft. So over here they're saying hysteresis is a term that refers to an internal compliance or lag in response of the shock to inputs. Hysteresis generally results from improper balance of pressures in the shock that overcompresses the internals. So that's something important to take from that. So they're saying that it's from the improper balance of pressures in the shock that overcompresses the internals. So that's what Penske say about it. But I also think it's important to sort of have a look at this other one here. So this is by Simon Emmons. So this was in 2007. He's done this research paper. So he's got a Masters of Science in Mechanical Engineering, and he's done this 135-page research paper, and they're talking about hysteresis and how it increases as the frequency increases. So if you get a chance, I would definitely recommend taking a look at that research paper. There's heaps of valuable information in that, and it's easily accessible. But so he talks about hysteresis in his paper, and he says that hysteresis is normally related to a loss of energy in a system, but in a damper, hysteresis relates to the energy that is being stored. This stored energy can be attributed to the compressibility within the damper. The compressibility can be classified into three different groups: elasticity of the damper parts, compressibility of the oil itself, and compressibility of the gas in the oil. Also, the gas volume causes a hysteresis effect. He goes on and he talks about this other study, and he says other studies attributed hysteresis to valve effects, valve flow, opening and closing, and friction. Hysteresis is not desired in racing dampers or any damper, but is rather a problem because it delays the build-up of output force. So we can see so two different bits of paperwork there. So he's saying here this study, they believe it may relate to valve flow and opening and closing, and he's saying here that it delays a build-up of output force. So back to what Penske said as well, that it's a delayed response of the shock. So we can see that everyone's sort of on the same page and talking about the same thing. So it's also worth taking a look here. So most guys would have seen this, but this is just your standard force velocity graph. We can see this is a nice clean one because it will be the averages. We've got the nose at the start. That part of the graph is attributed to the bleed circuit, and then you've got the knee. So depends what you want to believe, but most of the big suspension companies say that the knee is the portion of the graph that represents the shim stack lifting, and that the bulk of the slope is made up of the actual piston geometry itself. So yeah, you make of that as you will, really. And then we're going to look at this other, so this is obviously a bit of a representation, but this, we can see here we've got a damper with really severe hysteresis. So you can see on the way up, the damper is producing less force than as it deaccelerates from peak force. So that's what happens when you have high hysteresis. And we can have a look at these other two sheets here, and we can see we've got a damper which has very, very little hysteresis, and then we have a case where it's extremely bad, and you can see the big gap between the shock accelerating and deaccelerating. And so that's something to take note of, that when we have this hysteresis, that the shock feels like it behaves in a very progressive manner. So you get that, you know, that big build up of pressure later in the movement of the shock shaft, or, you know, damper rod of your fork. So okay, so next I think we're going to take a look at this force versus displacement graph and force versus velocity graph. This is a good example because we can see how they relate to each other. So obviously there's a bit of hysteresis in this damper as well, so you can see a gap between the accelerating force and the deaccelerating force, and how that represents on the force versus displacement graph. Obviously, as that gap widens, we see the shape of the force versus displacement graph move to the right. And then over here from the research papers, we have some test data. We can see the same thing. So we can see on this that as the frequency of the shock increased, so did the hysteresis. So you can see how it relates to the force versus displacement graph, and you can see how the shape of that force displacement graph changes as the hysteresis gets really severe. So that's a good case there. The next thing I wanted to have a bit of a look at is this graph that I spent a couple of days working on. So this is just, it's not really based off anything. I've used the WP shock data or numbers to configure it. So 6.7 to 1 ratio between the compression adjuster and the main piston. And what I've plotted on the blue adjuster line and the orange main line is an ideal damper. So if we look at it, we can see that everything's timed perfectly. So the first steeper lines represent the bleed circuits, and then we have the shim stacks opening, reaching their max deflection, and then the piston port geometry taking over. So on this perfectly balanced shock, we can see that at 200 psi our bleed circuits are sort of maxed out and our shim stacks start to open. Then we come over to 300 psi and the shim stacks have maxed out their deflection, and then it's down to piston port geometry. The important thing to note here is that this is pressure or time, so we can see that everything's happening at the same pressure or time. So I mean, I've got there 500 psi, so 37 mil of oil flowed out the compression adjuster at 500 psi, and 248 mil out the main piston at 500 psi. But I mean, that could represent time as well. We could say that was 50 milliseconds, which would represent a shock moving at 2 meters a second, 100 mil a stroke. So yeah, that's what an ideal damper would look like. Everything's happening at the same pressure and time, and you'd end up, with a good pressure balance. So then, if we have a look at some of these other lines here, I've got this grey line. So that represents a compression adjuster stack that's 25% stiffer. So obviously now, if we're using the orange line for our main piston, against the grey line for the compression adjuster, we can see that there's a delay in the shim stack lifting. So we're now 250 psi before we start to get any shim stack lift. So it's trailing the main piston, and then we come across to where we have our max deflection on our main piston, but we're still only halfway through the process on the compression adjuster. So we can see that we're going to have an increase in pressure in the compression chamber and increase in pressure in the rebound chamber. And then if we come over to our 248mm, we'll see that we haven't actually completely flowed our 37mm out the compression adjuster, so there's still that trail there. So yeah, you can see how it increases the pressure in the compression chamber and the rebound chamber, and it causes that lag. So the next line we're going to look at, we're going to go back to the blue line on the compression adjuster and follow the yellow line on the main piston. So yellow line represents 25% stiffer on the main piston, and we can see so that the point at which the shim stack starts to lift, again the timing's off, but this time it's a delay in the main piston, and we can see that I've actually experienced this myself and ruined a shock body in it. In this case you get into the risk of cavitation, so we are now flowing more oil through our compression adjuster relative to what we require through our main piston. So those numbers aren't lining up, and if we follow the main piston through to the point at where the shims are at max deflection, we can see that we have surpassed that point on the compression adjuster. And if we follow the yellow line all the way to what represents 248mm at the end here, we can see we to push 248mm through the main piston, now we require 607 psi, and at that pressure we far surpass the compression adjuster. So then I decided to plot the high flow piston so we can see why that might ride stiffer. So this little blue dotted line at the bottom here, and we can see again we've obviously altered the timing. So this time the shim stack's lifting, so I've worked off the concept that this piston has 30% more area working on the shim stack, so it's got the same shim stack on it, but it just has the same pressure applied to 30% more area, which obviously means the shim stacks will lift earlier and the thing's going to flow more oil. So we follow it up, we can see that we do have the shim stack lifting earlier. We come up to the second line where the shim stack's maxed out its deflection, and we can see that we have only just started to open the compression adjuster stack. So what that means is we are essentially operating like excessive head pressure because our main piston is got a way higher flow rate than our compression adjuster stack, and we're not producing the pressure in front of it to act on the stack. And then if we follow it right through to the end, so this little dot at the end, so that's calculated out at that would represent 248 mil of oil. So we did 248 mil of oil at say 350 psi, and unfortunately we're nowhere near the requirement we need to drive the 37 mil of oil out the compression adjuster stack. Like we're 150 psi behind. So what we're going to end up with there, and this is the thing, this is where Penske and all these other guys talk about it, is we're going to essentially be trying to compress the whole shock body. So the lag in the compression adjuster assembly is going to cause a build-up of pressure in the compression chamber and rebound chamber, and we will be trying to compress the entire shock because we just haven't produced sufficient pressure to pass the oil out the compression adjuster, and we are basically trying to hydraulic the shock. Now, the interesting thing is, they talk about how it increases with frequency, and that is the thing. Like, you can only imagine that if our active valve is 30% faster than our passive valve in terms of flow rate, um, that's only going to increase with the frequency. So it'll just get worse as the speeds increase. So that's, yeah, I think that's something to have a look at. So I've got it's a pretty average drawing, but it's represents peak pressure, and like we saw in those graphs from that research paper, so that peak pressure, depending on how we balance these valves in these scenarios, that peak pressure will shift either direction. So when you get that bad hysteresis that we saw in the examples, and like what we would experience with this high flow piston, that peak pressure tends to shift to the right. So that's that build up of pressure, and that's that build up of damping force as well, because at the end of the day, it's my belief that the force exerted on the end of the rod is just the pressure applied to the top of the main piston minus the force or pressure applied to the bottom of the piston. So if you delay that, then you're just going to end up, like I've mentioned earlier, with a shock that feels very, very progressive and stuff. And that's why, I've experienced it firsthand. When you get this balance off, when you use that high flow piston, or you have too much float on your mid valve on your forks, you actually end up using less travel than a well-balanced shock or fork. So that's something that we need to sort of keep in mind, and worth noting. And the other thing I wanted people to do is have a bit of a look. So I dug up some patent numbers. I think this is well worth checking out as well. So the old controversial BFRC shock. So the first patent was in 2010. The patent number for that is 8857582. That's worth looking at. And then the second patent, which will be, it looks like it's the RMZ shock, so that was in 2017, and it's patent number 10203013. You need to look at those, because the whole intention of those two shocks, or it's essentially the one shock, is to produce a shock that maintains its damping profile regardless of its frequency. And they're doing that because by using the plunger rather than the main piston, and only using the one, I think they call it a damping force, what do they call it? Damping force generator, they call it. They can maintain the pressure in the rebound chamber is always equal and only equal to the bladder pressure. So there's no variation in that. So they are producing a shock that's simply, the force is just a measure of the pressure applied to that plunger. So that's worth looking into. It'll give you some idea of where everyone's at with that. So I think I'm going to leave it at that for now. I might come back with another one where I start talking about shims and what I think we should be doing with those. In terms of, I think we're past the point of crossovers and thinking that changing one shim here and one shim there is going to alter the damping profile, when ultimately the damping profile is made up of piston port geometry and timing of events. So if you guys are keen to hear that, let me know. Otherwise we'll leave it at that. Thanks.